In uniform motion problems, we're going to have two things moving, maybe the same direction, maybe different directions, maybe the same speed, maybe different speeds, maybe the same distance, maybe different distance, and we're going to need to solve. So the big things in these is always the setup. So it's very helpful to make yourself a table. And some people prefer to say rate instead of speed, whatever you prefer. But if we remember that speed is distance divided by time, or rate times time equals distance, sometimes we say it's the DIRT formula, distance equals rate times time, then we can make these tables that give us a beautiful little equation for our two things that are moving. So we're going to have a speed times the time equals our distance, or our rate times time equals distance. And we want to set these up. A uniform speed or uniform motion means we're assuming they magically stay the exact same speed the whole time. And then we are going to, in this table, look for what we are solving for, what we know is equal, and what we don't know yet. So let's look at how this works. We have a problem here. Two motorcycles are driving towards each other from opposite ends of a freeway. So they're coming this way. And that freeway is 710 kilometers altogether. The first motorcycle is going 37 kilometers per hour, and the second motorcycle is going 34 kilometers per hour. And how long is it going to take until they pass each other? So right now we're missing a lot. We have some speeds, we have no time, no distance. We do know, though, that if they're going on opposite ends of a 710 kilometer freeway, then when they meet up, they will have gone altogether 710. So we know whatever these two things are, when we add them up, we will equal 710. Helpful. And when, assuming they start at the same time, which is what they told us, when they pass each other, that happens at the same time for both motorcycle riders, right? So it's going to happen at the same time. So they're driving for the same amount of time. So that's what I'm going to put in as my X here. I could put in X's distance, but this just feels like it's going to be easier this way. And I'm going to remember speed times the time equals the distance. So now that I know my time is X, and actually another good reason to put X in for the time is that the question is asking how long will it take, right? The question is asking for time. So helpful to put X in exactly where the problem's asking for it. So now using speed times time equals distance. 37 times X is 37X. That's how far the first motorcyclist went. And then 34 times X tells me how far my second motorcyclist went. And now in this particular problem, I know that their two distances added together give us 710. So now I have an equation I can set up and solve. You will see other problems where their distances are equal. And again, like we would just have a slightly different equation to set up and solve for those. The hardest part every time is the setup. When I divide by 71 on both sides of this, I'm going to see that X equals 10. So in this extremely magical problem, these motorcyclists are driving for 10 hours straight, never changing their speed, never stopping to go to the bathroom until they pass each other. Truly absurd, but does help us practice setting up and solving algebraic equations. Let's do another. Immediately harder. We now have a boat that is rowing downstream with the current and then upstream against the current. We know they went 110 kilometers both ways. It's like the same distance, right? They go there and they come back. Please remember, downstream is always going to be faster, which means it takes less time. And then upstream is always slower. You're going against the current, which means it takes more time. That's just, sometimes people get those twisted when they're setting up. All right, so downstream with the current took 7 hours. And then that same distance upstream took 17 hours. All right, we know speed times time equals distance. So if I need to go backwards to my speed, I'm going to say my distance divided by my time will give me my speed. And if you ever have trouble remembering that, just remind yourself that we drive in miles per hour or kilometers per hour. And so that's always distance per time. So that's a helpful way to remember that. 119 divided by 7, we were going 17 kilometers per hour here and 7 kilometers per hour here. So helpful, but the question asks, what is the crew's rowing rate in still water? So what were they doing if there was no current at all? So their rate, I'm just going to call it X today, plus the current, so going faster, was 17. And their rate taking away the current, like the current working against them, was 7. So depending on where you are in your math journey, there's different ways to look at this. We could look at this as systems of equations and solve these two different equations using systems. Elimination's a really easy one here. If you haven't done systems of equations yet, what I like to remember is the current is the same either way, right? So what we have here is my 7 and my 17, and I was going plus the current minus the current. And what I need is that number smack dab in the middle. I'm like, what is exactly between 7 and 17? And so we're going to find the average right in between 7 and 17. And to do that, we just add them up and divide by 2. So when we do that, we'll get 24 over 2 is 12. And we'll double check. Is it true 12? It's plus 5 to go this way, and it's minus 5 to go this way. Yes, that works. So their rate in still water is 12 kilometers per hour. And if anyone cares, the current was 5 kilometers per hour. Really fast, if you do know how to do systems, let's solve this with systems. If I just do elimination, I have one positive C and one negative C here, so I can just add everything up. And I've got 24 and 2x, and those guys cancel. And I go x divided by 2. It's the exact same steps as doing it without systems of elimination, or solving systems with elimination. But it just depends on which way it's more helpful for you to think about it. Okay, currents are definitely the worst ones. Let's try another one, though, because these are all hard. Christopher and his parents live 115 miles apart. I'm just going to start with a picture, okay? Christopher, parents, this is 115 miles apart. They meet at a restaurant in between their homes. So we're meeting up somewhere in here. Maybe it's the dead center, but probably not. Christopher drove 1.5 hours, and his parents drove 1 hour. His speed was 10 miles per hour faster than his parents' speed. How fast did he drive? Ooh, you know what? I just set that up as x plus 10, but I would like to change that already because I just noticed, oh no. All right. Christopher and his parents live 115 miles apart. I'm going to start with a picture. We've got Christopher, we've got his parents, they're 115 miles apart. They meet at a restaurant in between their homes, so somewhere in here, who knows. Christopher drove 1.5 hours to get to the restaurant, and his parents drove 1 hour. Christopher's speed was 10 miles an hour faster than his parents' speed. How fast did he drive? So since my problem is asking me, how fast did Christopher drive? I'm going to put that in as my x because that's the thing I want to know at the end. I know his parents, he drove 10 miles per hour faster than his parents. So that means his parents were going 10 slower than him. And what do I know about distance? I know that all together, like Chris's drive plus his parents' drive, made 115 miles. So this plus this equals 115. Okay, speed times time equals distance. This is just 1.5 times x. And multiplying by 1 is so nice. This is just x minus 10. Okay, let's set it up. Ooh, actually, I'll just use this one. Equals 115 I already have. 1.5x plus x minus 10 equals 115. We're going to combine like terms. Isolate that x. And we are going to divide by 2.5 to get x all by itself on one side. How fast was Christopher driving? X is 50. So Christopher was driving 50 miles an hour. His parents were driving 40 miles an hour. It looks simple to watch. It's so much harder to do. All right. If you're feeling confident, pause the video, try this all by yourself. If you're not, stick with me. It's fine. When Katie walks to school, it takes her 30 minutes. And when she rides her bike, it takes 15 minutes. Her speed on her bike is 3 miles per hour faster than when she walks. How fast does she walk? That's what we're looking for. So I'm going to put my X right here for how fast does she walk. Now I need to be careful in this problem. Her speed on her bike is 3 miles per hour faster. So since this is in miles per hour, I need to make sure this is also in hours. So I'm going to change 30 minutes to be half of an hour, 0.5 or 1/2 if you prefer, and 15 minutes to be a quarter of an hour. All right. What do we know about the distance? Nothing explicit. However, we know she is walking to school and she is riding her bike to school. We can assume her home and her school are not moving. So these two distances should be the same. They should be equal to each other. All right, let's multiply it out and solve them. Speed times time equals distance. 0.5x and then 0.25 times x plus 3. Those two are equal. Let's set up our equation. Equals. Okay, I'm going to distribute. Let's see, half of 3 is 1.5, so a quarter of x should be 0.75. I'm going to move all my x's to the other side of the equation. And when I divide by 0.25, I should get x equals 3. What was x? Let's come back to the top. X was how fast she walks. So she walks 3 miles per hour. And when she bikes, she's biking 6 miles per hour. Okay. Let's try another. A commercial jet and a private airplane both fly from Denver to Phoenix. Okay, that tells me these are equal. They're both flying the same distance. The commercial jet takes 1.1 hours and the private airplane takes 1.8 hours. The speed of the commercial jet is 210 miles per hour faster than the airplane. Find the speed of both airplanes. So in this one, I get to choose what I want to be my x. It doesn't entirely matter. So I'm going to just say, since I know the jet is plus 210, I'll put that like this. Have my airplane be x. All right, my distances are equal. Speed times time equals distance. So I have 1.1 times x plus 210. And down here I have just 1.8x. I'm going to use the fact that I know my distances are equal to set up this equation. All right, distributing. What is 210 times 1.1? 231. Well, of course it's 231. It's 210 and 21. We're going to move all the x's to the same side of the equation. And we're going to divide by 0.7 to get x all by itself. And when we do that, we get 330 is x. But now, come back to your problem. What's x? X is my speed of the airplane. So the private airplane is going 330 miles per hour. And the jet is going 330 plus 210, 540 miles per hour. All right, trying just a few more. Let's do another current one. We've got a tugboat going upstream, slower, and then downstream, faster. They go 33.6 miles, and then the return trip should be the same. Upstream took us 14 hours, and downstream took us 4. So we did this just like this before. Let's try it again. We're going to go distance divided by the time to get our speed. And gosh, what is that? 2.4 miles per hour. And then 33.6 divided by 4 gives us 8.4 speed for our downstream miles per hour. So again, you can think about what is the middle point exactly between 2.4 and 8.4. And that middle point is always going to be if you add them up and divide by 2. 10.8 divided by 2 gives us 5.4. So that is our speed without a current. Speed of the tugboat without a current is 5.4. And then the current is however much we need to get in between these two. And it looks like this is a +3 and this way is a -3. So tugboat, 5.4 miles per hour, and the current, 3 miles per hour. All right, one last one. Dawn and Skylar leave the park at the same time in opposite directions. All right, think about we're going away from each other. If Skylar travels 7 miles per hour faster than Dawn, and after 5 hours, excellent, 5 hours, they are 115 miles apart. So right here was the park. Here went Skylar, and here went Dawn. And now this total distance is 115. So that's this plus this equals 115. How fast is each one traveling? So it doesn't matter where we put our x. It could be Dawn or Skylar. Skylar's traveling 7 miles per hour faster than Dawn. So let's call Dawn x and Skylar x plus 7. All right, let's see what happens. Speed times time equals distance. 5x and 5 times x plus 7. We know those add up together to 115. So we're going to solve, distribute out this 5. Combine like terms. Get that 10x all by itself. And then get x all by itself. And it looks like, who was x? Dawn was traveling 8 miles per hour. And Skylar was traveling 8 plus 7, 15 miles per hour. All right, Sean left 1 hour before Lacey, traveling in opposite directions. We're again going like Sean this way, Lacey this way. I made Lacey's arrow bigger, but I'm not actually. Oh yeah, looks like that's probably right because she went faster. All right. He averaged 29 miles per hour and she averaged 48 miles per hour. I was about to say my arrows are not necessarily indicative of the problem, but they were okay this time. How long had each been driving when they were 183 miles apart. So these two things, these two arrows are adding up to 183. And we're looking for the time. Now, when we are driving apart from each other or towards each other, whichever way, and we're getting to a point where we're a certain distance apart, that time is the same for both of us. So the time is identical in these. 29x. Ooh, back up, Lindsay. That is not accurate. All right. The other thing we know here is that Sean left 1 hour before Lacey. So he's traveling 1 hour longer than she is. And Lacey's time we'll call x. And so that Sean's going to be x plus 1. Now we're going to go speed times time equals distance. 29 times x plus 1 and 48 times x. Those two things together are going to add up to 183 miles. So let's start solving, huh? Distributing out my 29. Let's combine like terms and get my x's together here. Move my 29 to the other side now. We get x equals 2. Now careful. What was x? That's how long Lacey was traveling. So she was moving, however they were moving. I'm assuming driving. Certainly wasn't walking 48 miles per hour. So she was, driving for 2 hours. And Sean, since he left 1 hour before, was driving for 3 hours. All right. Nicholas left a party traveling 5 miles per hour. And 3 hours later, Jayla decides to go catch up with him. She's running 6 miles per hour. How long is she going to have to run to catch up with him? We're a little worried right now. We don't have, there's a lot we're missing. Well, the thing we want to know is how long Jayla is running, right? So that's going to be my x. I know that Nicholas left the party and then 3 hours later, Jayla came out. So Nicholas has been out there 3 hours longer than Jayla. And if she is catching up to him, that means our distances are equal. They're now at the same location and they left the same party. So now we'll do our speed times time equals distance, 5 times x plus 3 and 6 times x. And we'll set these guys equal to each other and figure out just how long Jayla has been running to catch up with Nicholas. Oh God, these problems are absurd because look, we've got 6x minus 5x leaves me just 1x. So my answer is 15, which means Jayla in this problem has been running for 15 hours. And Nicholas has been, run walking for 15 plus 3, 18 hours. Crazy, absolutely absurd. But given the ridiculousness of the problem, true here, normally I would always tell you, stop at the end and go, does this even make sense though? Would I run for 15 hours to catch up with my friend after he left a party? No, I would not. In this case, unfortunately, if you're doing MyOpen Math, uniform motion problems, you may find yourself in absurd situations like this. Normally, it is always good to think, does this make any common sense? And listen, this one doesn't, but it is consistent with the problem. If Jayla's running 6 miles per hour for 15 hours, she's going to end up running 90 miles. And if Nicholas was traveling 5 miles an hour for 15 plus 3, 18 hours, he's also going to end up traveling 90 miles. So I guess it worked technically. Did it make sense? No.